a sphere and assign a scripted controller to the position track, a position script. In this scripted controller, we're going to enter 100 times cosine of the current time, 100 times sine of the current time, and 0. If we would evaluate now, the controller will let the sphere move in a circle, and at frame 90, since we're using the current time as the angle, at 90 degrees it reaches the top of the circle. We're going to enable the trajectory in order to see the result. It is a good idea to scale the scene to contain more frames. Now we can see that as we increment the time, the sphere is moving in circle. The multipliers that we use define the radius along the x-axis and the radius along the y-axis. So if we would change the second multiplier to, for example, 50, we would get an elliptic trajectory instead of a circle. Right now we're using the origin of the coordinate system as the center of the rotation, but we can offset the center by adding the coordinates of the center to the x, y, and z. For example, if we want the center to be at 30, 20, plus 10, we can evaluate. And now, looking at this rotation, the sphere is moving 10 units above the ground plane, and the center is located at coordinates 30, 20. The vector dot product is very often used in computer graphics. Its geometric interpretation is the projection of the second vector onto the first one. This involves the multiplication of the norms of the two vectors with the cosine of the angle between them, but this is the mathematical definition which you don't have to remember or understand. It's more interesting to see how the vector dot product can be used in practice. Obviously, when the two vectors are perpendicular, defining an angle of 90 degrees, the projection of the second vector onto the first one, or the other way around, it's always going to be 0. If the two are parallel, then the projection is equal to the vector itself. When the angle is 180 degrees, they're pointing in opposite directions. The angle is 180 degrees. The cosine of the angle is -1. But what is very interesting in this case is that if we would normalize both vectors to have a length of exactly 1.0, the endpoints of the vectors would lie on the unit circle that we saw when looking at the sine and cosine functions. This means that the projection of the one vector onto the other would be exactly the cosine of the angle between the two vectors. This means that we can easily calculate the angle between any two vectors by just normalizing them, calculating the vector dot product, and then calculating the inverse of the cosine function, which is easy. For example, if we have the cosine of the angle 45 degrees, the inverse of the cosine function returns the angle corresponding to that cosine. So now we can set the angle between the two vectors to, for example, 45 degrees, and then take the position of the one point and define a vector 1. Define a vector 2 from the position of the other point. And then calculate the dot product of the normalized vector 1 and vector 2. And finally, calculate